Okay, so good afternoon, everyone. I will talk about an Agda library that I've developed, and that's called Sikkel. So what's the general purpose of this library? Well, dependently typed programming language like Agda or COP are based on mathematical type theories like Martin-Löf type theory or the calculus of inductive constructions. And over the past years, a lot of formal systems have been developed that extend such standard type theories with new primitives, and those new primitives allow you to write more programs or to prove more properties. We included some examples here in the slide. But the question is, well, all of these formal systems have been developed on paper, but how can we work with them within our proof assistants like Agda or COC? We actually want to use these new primitives when programming with Agda and COC. And Sikkel is a first step towards that goal. So here you can see a general overview of the architecture of our library. So as you can see, Sikkel consists of 3 layers. And the first layer is a syntactic layer. So it provides a syntax of multimode simple type theory. Don't worry about that term. I will come back to it on the next slide. So it provides a syntax, and that syntax can easily be extended with new primitives. And so at this layer, you can write your programs in the syntax and can make use of these new primitives. What you cannot do at this layer is evaluate your program. So there is no notion of computation or reduction of a program to a value at this layer. But what you can do is you can compute the meaning of your program at the second semantic layer. So this semantic layer consists of a formalization of presheaf models in Agda. So presheaf models are a well-known and broad class of models of type theory. And so if you've written a program P at the syntactic layer, Sikkel's type checker will verify whether your program is well typed. And if it's successful, it will automatically give you the denotation of that program in a presheaf model. And the third layer is kind of the meta level. It's actually the programming language Agda that we're using to implement all of this. And so the denotation of some programs can be extracted to actual Agda programs, to real Agda functions that can then be imported and used in other Agda developments that do not necessarily make use of our library. So for the rest of this presentation, I will go over these different layers, over all of these different components, and we'll start with the syntactic layer. So this multimode simple type theory, there are 2 things to note here. The first one is that it's simple type theory. So for the moment, there is no support for dependent types at the syntactic layer, and there's also no support for polymorphic types like for all x, x to x. And second, it's multimode type theory, and that means that MSTT is parameterized by the so-called mode theory. And such a mode theory is actually just a small category whose objects we call modes and whose morphism which we call modalities. And if you fix such a mode theory, then Sikkel will provide you Agda data types that represent types, terms, and contexts of the object theory of MSTT. And all of these Agda data types are indexed by a mode. So every type, every term, every context in MSTT lives at a particular mode. Moreover, MSTT is extrinsically typed. So for instance, this Agda data type term expression is not indexed by a type or a context. And furthermore, for every modality new in our mode theory that goes from mode M to mode N, we get a new primitive type constructor that transforms a type T at mode M to a type mu T at mode N. And in the opposite direction, we also get a primitive operation on contexts that transforms a context gamma at mode N to a context gamma log mu at mode N. And you can think of this log operation as kind of a left adjoint to this type constructor. So you can go back and forth between terms of type mu T in context gamma and terms of type T in context gamma log mu. So I will not go over all of the typing rules of MSTT, but I will try to show you how you can write programs in it by means of an example. So suppose we have the following mode theory. We have 3 modes M and O, a modality mu from M to N, and a modality kappa from N to O. And then we're going to write a function of the following type. So this circle M is composition of modalities. Recall that modalities were morphisms from a category, and so they can be composed. And the function of this type is kind of an applicative operator for the modality kappa, specialized to modal functions of type mu a to b. So to write such a function, we start with the empty context. We need to use a function of this type. It's a modal function. Its argument has modality kappa. So we're going to use modal lambda abstraction for that. And as you can see here, variables in MSFP are represented by strings. But that's not a problem, because at the syntactic layer, we're not going to evaluate programs, and all of these variable names will be eliminated when we interpret a program at the semantic layer. So the effect of this lambda abstraction is that we extend our context with a variable, and as you can see here, every variable occurs in the context under a certain modality. So this variable occurs under the modality kappa because we used modal lambda abstraction for modality. And now we still need to produce a modal function, this time with modality kappa composed with mu. So we again use modal lambda abstraction and again extend our context with a new variable. And then we need to produce the value of the modal type kappa b. And for that, we can use the modal constructor mod kappa. And recall that this lock operation on context was kind of a left adjoint to the modal type constructor. Well, this mod kappa actually is part of that adjunction. So it allows us to construct a value of type kappa b by giving a value of type b after locking the context. So now we need to give a value of type b, but we've locked our context with the modality kappa. How are we going to produce such a value of type b? Well, we actually want to apply this function f to the variable a. We cannot directly do that because f is a modal function, it has this modality mu in its type. So we're going to use modal function application. It lets us apply this function f, but the argument will then be type checked in a context and is locked with this modality. So now we want to fill in this variable f here in hole number 0. There is one condition we need to check though, and that's because in MSCT you can only use a variable in a term when the modality under which it appears is equal to the modality, the composition of all the modalities in the locks to the right of that variable. So in this case, f appears under modality kappa. There is only one lock to the right of f, which is also of modality kappa. And so indeed, we can use the variable f at this point. Same applies for variable a. We want to use this variable a here. It appears under modality kappa composed with mu, but there are two locks to the right of it, whose composition is again kappa composed with mu. So indeed, we can use this variable a at this point. So now we know how to write programs in MSCT. So let's now look at a concrete application. So in this presentation, I will talk about guarded recursion. And to do that, I will first briefly discuss how you can work with infinite streams in Agda. So you can define a type of infinite streams as the following co-inductive record type. So we say that a stream of A's consists of a head of type A and a tail, which is again of type stream A. You can then construct you can construct such streams as by using co-pattern matching. So for instance, to create the stream of the infinite stream of zeros, we say, well, the head of that stream is just a number 0, and the tail is again the stream 0. So when defining the tail of such a stream, we can co-recursively refer to the stream that we're defining. And the same principle applies when defining a function that produces streams, such as this map function for streams. But we need to be careful in the same sense as in the same way as we need to be careful when writing functions by recursion. Then we must make sure that all these functions terminate, and that will be checked by Agda's termination checker. Well, in the same way, we must make sure here that every definition of a stream is productive. So, and that means that every element of that stream can be computed in a finite amount of time. And Agda will also check that with a productivity checker. But that productivity checker is sometimes quite restrictive. For example, here is the definition of a stream of natural numbers. We say the head of that stream is just a number 0, and the tail is obtained by mapping the successor function to this stream of natural numbers. But that definition is not accepted by Agda's productivity checker because we apply this function maps up to the result of a co-recursive call. And that's not allowed. The only functions that may be applied to a co-recursive call are constructors like tail. And even then, it's not guaranteed that your function will be productive, but it's definitely not allowed to apply an arbitrary function to a co-recursive call. However, this definition actually is productive. You can see that in this diagram. So we begin with a stream that starts with a 0. We just apply a successor function to get the second element, and we do that again and again, and we see that every element of the stream can be computed in a finite amount of time. But if we replace this function mapSec with the function flip first that flips the first two elements of a stream, then we do get into trouble. Because in this case, we again begin with a stream that starts with a 0. We can easily compute the third element of that stream and the fourth element, but we have no clue how to compute the second element of that stream. And note that both functions, mapSec and flip first, can be assigned the type stream n to stream n like that. So there is no way to tell the difference between these functions in their type. And that's what guarded recursion will allow you to do. So in guarded recursion, you can express the different behavior between those functions in the type of these functions. So for guarded recursion, we're going to use the following mode theory. There is a mode omega, which is the time-dependent mode, and you can intuitively think of a value at mode omega as if it unfolds over time. It makes available a new piece of information at every time step. And there is a mode star, which is the time-independent mode, and so a value at this mode is just a static value. It does not unfold. And then there are three modalities, three important modalities. There is the later modality, which takes an unfolding value and just delays that unfolding process by one time step. So everything that would be available today is now actually only available tomorrow. There is a constantly modality that takes a static value and makes an unfolding value out of it that actually does not unfold. So everything is available from the beginning. And there is a forever modality that takes an unfolding value and makes everything available at once by just applying this unfolding forever. There are also some equalities between these modalities, but those will not be important for this presentation. Now, on top of this mode theory, we also add some new non-modal type and term constructors. So first we add a type for guarded streams. So a type constructor for guarded streams, it takes a type A at mode star and produces a type G stream A at mode omega. And a guarded stream can be intuitively seen as a discrete signal that produces one value at every time step. And so the tail of such a guarded stream will have type later guarded stream and not guarded stream, because well, that tail will only start to produce a value tomorrow and not today. And finally, we also add a term constructor for loop induction. Loop induction is an induction principle from guarded recursion, and it allows us, when constructing a term of type t, any type t at mode omega, it allows us to use a variable of that type t that is in the context under a later modality. So that variable will stand for a co-recursive call, and the fact that it appears under the later modality will prevent us from writing non-productive definitions. I should notice that this later here does not refer to the later modality, but it is actually part of the syntax for this induction. So with this system, we can write a function, a guarded, well, not a function, we can write a definition of a guarded string of natural numbers that is accepted. So again, we start in the empty context. We want to use co-recursion, so we're going to use loop induction, and that extends our context with a new variable s. Now we still need to produce a guarded stream of natural numbers, and we're going to use cons for guarded streams to do this. So this cons is a modal function. It takes this argument with a constantly and a later modality. So we're going to use modal function application here. Now we need to produce the head of our stream. That will be just the number 0. And that's actually a valid term in any context, so we can just do that. And now we need to provide the tail of our stream, and we've locked our context with a later modality. What we want to do is we want to map the successor function over this co-recursive call. So we're going to use a map function for guarded recursion. The implementation of that function can be found in the paper, and it takes a function from A to B under this constantly modality. So again, we use modal function application here, and at hole number 1, we now need to give a function from that to that. That will just be the successor function, and that's also a valid term in any context. And now we want to, in hole number 2, we want to refer to this co-recursive call. So we're going to use this variable s bound by loop induction. The question is, can we use that variable at this point? And the answer is yes, because it appears under the later modality, and our context is also locked by the later modality. So this is a definition of a guarded stream of natural numbers that is accepted. The question is then, what happens if we replace this gmap of suck with flip first? So we can write a guarded version of this flip first function, but it will only have type gstring_nut to later gstring_nut, and not gstring_nut to gstring_nut. So this definition, if we replace gmap suck with g flip first, it would give you a definition that does not match. Okay, so now we have a guarded stream of natural numbers, but these guarded streams are actually behave quite differently than Agda streams. One important difference is that they have this later modality in their tail, in the type of their tail. But we can, in MSFP, we can define a new type constructor stream prime of standard streams that behave much more the same as Agda streams. And we can do that by just applying this forever modality to the type of guarded streams, and we end up with the type at mode star. And we can then use this modal constructor to produce a standard stream of natural numbers in MSFP. Okay, so we've talked about this syntactic layer. Let's now go to the semantic layer. The first question is, why do we need a semantic layer? Why can't we directly interpret programs at the syntactic layer as Agda programs? And the problem is that we want to work in an off-the-shelf version of Agda, which does not support these modalities or these new primitives. And so interpretation of these new primitives would be very hard or even impossible to do better. And so this semantic layer consists of a formalization of presheaf models in Agda. And so to get an intuition about what a presheaf is, we're going to look at the interpretation of this type of guarded streams. So we call it a guarded stream, can be thought of as a signal that produces a value at every time step. And so what we're going to do is, at every time step, we're going to keep track of all the information that's present until that point. And so right now we have one value that we collect in a vector of times 1. After one time step, we have 2 values, which we collect in a vector of times 2, and so on and so on. And so we get this sequence of Agda types with these init functions between them. Such an init function drops the last element of a vector, and so it tells us how we need to forget the newly available information when going from time step n+1 to time step n. And if we represent types as such a diagram, it becomes really easy to interpret the later modality, because then we just shift everything to the right, and we add a unit type which contains no information to the front. And it also becomes easy to interpret loop induction, because when we try to define a guarded stream by loop induction, we can use a variable of type later gstring in a context. So we get a situation like this. And now we need to produce values of all of these Agda types, but that's easy because you can start with this unit modality that has just one element. Yeah.
Oh, sorry. The mode theory didn't say that they were indexed by natural numbers, right? Like there's multiple different presheaf categories you can interpret the mode theory.
Yeah, I will come to that. So we start with this value of the unit type. We construct a vector of 1 out of it. We use that vector of 1 to construct a vector of 2, etc., etc. And so, as you can see, by representing types as diagrams of this shape, we can easily interpret these new primitives like the later modality and loop induction. And so, in general, the presheaf model, in a presheaf model, context and types are interpreted as these kind of diagrams, like these two, but they might have a different shape. And so, in general, a presheaf model is parameterized by a base category. That base category determines the shape of these diagrams, and the shape of these diagrams in turn determines what new primitive operations can be interpreted. And so in general, a mode will be interpreted as a base category. So that partly answers your question, and the second part of the answer will come in a few slides. And a context in that mode will then be interpreted as a presheaf over the corresponding base category. Types are interpreted as dependent presheafs, terms as dependent presheaf morphisms, and modalities as dependent private joins. And so that basically means that there should be semantic analogs of these modal type constructor and log operation. And also notice that semantic types can depend on variables in a context. So at this layer, there is already some form of some support for dependent types. So we've looked at the first two layers. Let's now discuss the bridge between them, which is a sound type checker, and actually it's even a sound type inferencer, because there is an Agda function if we interpret that will take an MSTT context at mod n and an MSTT term t at the same mod n, and will then verify whether t is well typed in Gamma. And if that's the case, it will return an MSTT type capital T, and the denotation of this term t as a semantic term over the base category. That's the interpretation of this mode n with the right context and type. And so this type inferencer is easy to extend in the sense that when you want to implement a new type theory in Sikkel, you just need to specify how modes should be interpreted as base categories, and modalities should be interpreted as dependent by the joints, etc. And that brings us to the final part, and that is the extraction to actual Agda programs. But that will not always be possible. In fact, this extraction mechanism only works for a presheaf model with one particular base category, namely the trivial base category. The reason for that is that presheafs over its base category just consist of one Agda type and no non-trivial Agda functions. And so if you get a closed semantic term over this base category, all you have is actually just one Agda value, which makes it easy to extract to Agda, because we can just use this Agda value as the extracted Agda program. Now, it might seem restrictive, very restrictive, to only allow extraction from a presheaf model with one particular base category. But the idea is that the mode theory should contain modalities, and so there should always also be dependent by the joints at the semantic layer that allow you to transport definitions to this one base category. And an example is this forever modality for direct recursion. There is still one problem, and that's that Agda type, Agda values that are obtained in this way do not always have the intended type. For example, if you look at the definition of this standard stream of natural numbers, if you compute its denotation in a presheaf model, it will have a type like for all n a vector of length n plus 1, which is not exactly the type of Agda strings. It's isomorphic to it, but it's not exactly the same type. And so we solve this by introducing an extractable type class on closed semantic types. And instances of that type class will provide the intended translated type and also functions to apply this isomorphism. And so in this way, we can really construct an ordinary Agda stream of natural numbers that we can then further use as an ordinary Agda stream. So, as a conclusion, Sikkel allows you to work in a multimodal setting within an off-the-shelf version of Agda, and to also extract these programs as ordinary Agda programs. The syntactic layer is parameterized by a general mode theory, and it can also be extended with extra non-modal primitives. The semantic layer is fully general in the base category. We also illustrate this with another application in the paper that involves a restricted form of parametricity. And there is an extraction mechanism that crucially makes use of these modes and these modalities. As future work, we plan to support, to support dependent types at the syntactic layer. So what appears to be challenging is writing an interpretation function from a dependently typed syntax to a presheaf models that gets accepted by Agda's termination checker. So as an intermediate step, we're working on an extensible program logic that allows you to prove properties of Sikkel programs and also to extract those proofs to Agda proofs of extracted Agda programs. We're hoping to implement the Hoffman-Stack universe at the semantic layer, and are also intending to investigate other applications such as nominal techniques using our idea. So that was my presentation. Thank you.
Questions? So you use presheaf categories, right? And then do you implement all the theory about presheaf categories yourself, or do you use like a library for category?
I implemented it myself.
Why didn't you use the library for category theory instead?
Because, well, when I started this, I didn't know of any good library for category theory in Agda. And also this way, I can, well, we're not really anything to show in the slide, but I can use convenient notation to work with all of these things in Agda. And so that was certainly the case in the first iteration of this library, where it was actually intended to not have these three layers, but actually directly work on this semantic layer. And there it was really important to have convenient operations to work with this model in a kind of way, but you seemed like you were working in a syntax. So yeah.